Hey everyone, I hope you're doing well tonight and finding some peace as you wind down from your day. Tonight, we're going to embark on a gentle journey through the fascinating history of Linux, the open source operating system that quietly powers so much of our digital world. The year 1991 would prove to be a watershed moment in computing history, though few could have predicted it at the time. In a modest apartment in Helsinki, Finland, a 21-year-old computer science student named Linus Benedict Torvalds was growing increasingly frustrated with the limitations of his operating system. The young Finn had been using Minix, a Unix-like system created by Professor Andrew Tannenbaum for educational purposes, but its restrictive licensing and limited capabilities left him yearning for something more powerful and flexible. Linus had always been drawn to the intricate world of computer programming. Born on December 28, 1969, he had shown an early aptitude for mathematics and logic that would serve him well in the emerging field of computer science. His grandfather, Leo Turnquist, was a statistician and mathematician who introduced young Linus to the world of numbers and analytical thinking. This early exposure to systematic reasoning would prove crucial in shaping his approach to software development. The computing landscape of 1991 was dominated by proprietary systems that jealously guarded their source code. Microsoft was ascending to new heights with MS-DOS and the early versions of Windows, while Unix systems remained largely the province of universities and large corporations, their expensive licenses putting them out of reach for most individual users. The personal computer revolution was well underway, but the software that powered these machines remained locked away behind corporate walls. It was against this backdrop that Linus began what he initially described as a hobby project. On April 3, 1991, he purchased his first personal computer, a 386DX machine with 4 megabytes of RAM and a 40-megabyte hard drive. The computer came with MS-DOS, but Linus was far more interested in exploring the capabilities of the underlying hardware than in using Microsoft's operating system. His frustration with Minix's limitations reached a boiling point during the summer of 1991. Minix was designed primarily as a teaching tool, and its creator, Andrew Tannenbaum, had deliberately kept it simple and limited its capabilities to maintain its educational focus. Users were not permitted to modify the kernel, and the system's architecture was constrained by decisions that prioritized pedagogical clarity over practical functionality. Linus decided to create his own operating system kernel, one that would take full advantage of the 386 processor's capabilities and provide the Unix-like environment he craved. He began working on what he initially called FreeAxe, a name combining free, freak, and Unix. The project started modestly, with Linus writing a simple task switcher that could alternate between two processes, printing different strings to the screen. On July 3, 1991, Linus made his first public mention of his project in a post to the Comp OS Minix newsgroup. He wrote, "I'm doing a free operating system, just a hobby. Won't be big and professional like GNU for 386, 486, AT clones." This seemingly casual announcement would prove to be one of the most significant understatements in computing history. The reference to GNU in his post was particularly significant. The GNU project, launched by Richard Stallman in 1983, was an ambitious attempt to create a completely free Unix-like operating system. GNU, which stood for GNU's Not Unix, had developed many of the essential components needed for a complete operating system, including compilers, editors, and utilities. However, the project's kernel, called the Herd, had proven to be far more complex and challenging to develop than initially anticipated. Stallman's vision extended far beyond mere technical considerations. He believed that software freedom was a fundamental right, and he had developed what would become known as copyleft licensing to ensure that free software would remain free. The GNU General Public License, first published in 1989, was designed to prevent the appropriation of free software by proprietary vendors and to create a self-reinforcing ecosystem of shared code. Linus was influenced by Stallman's philosophical arguments about software freedom, but his approach was more pragmatic than ideological. He was primarily motivated by technical curiosity and the desire to create something useful, rather than by grand visions of software liberation. This pragmatic approach would prove to be one of Linux's greatest strengths, attracting developers who were more interested in solving technical problems than in advancing political causes. As the summer of 1991 progressed, Linus's kernel began to take shape. He worked with characteristic Finnish determination, coding late into the night and testing his work on his 386 machine. The early kernel was extremely basic, capable of little more than printing messages to the screen and reading from the keyboard, but it demonstrated the fundamental concepts that would make Linux successful. On August 25, 1991, Linus made another post to comp.os Minix that would become famous in the annals of computing history. He wrote, "I'm doing a free operating system, just a hobby, won't be big and professional like GNU for 486 AT clones. This has been brewing since April and is starting to get ready. I'd like any feedback on things people like, dislike in Minix, as my OS resembles it somewhat." This post was remarkable for its modesty and its invitation for collaboration. Unlike the secretive development practices common in the commercial software industry, Linus was openly sharing his work and actively seeking input from the broader community. He went on to explain that his system would not be portable to other architectures and would not support anything other than AT hard disks, but he was curious about what features people would want in an operating system. The response to Linus's post was immediate and enthusiastic. Programmers around the world began downloading his early kernel releases and experimenting with the code. The first official release, version 0.01, was made available on September 17, 1991. This initial release was barely functional, requiring users to have access to a Minix system to compile and install it, but it demonstrated the potential of Linus's approach. What set Linux apart from other hobby operating system projects was not just the quality of the code, but the open development model that Linus employed. Unlike traditional software development, which took place behind closed doors with small teams of programmers, Linux development was conducted entirely in the open. Anyone could download the source code, examine it, modify it, and contribute improvements back to the project. The name Linux itself emerged from this collaborative process. When Linus first uploaded his kernel to the FTP server at the Helsinki University of Technology, the administrator, Ari Lemke, decided that Freax was not a suitable name and instead created a directory called Linux. Linus initially objected to having the kernel named after himself, considering it too egotistical, but the name stuck and eventually became the standard. The early Linux community was characterized by its international and collaborative nature. Developers from around the world contributed code, reported bugs, and suggested improvements. This global collaboration was facilitated by the emerging Internet, which provided a platform for distributed development that had never before been possible. One of the most significant early contributors was H.J. Liu, who created the first Linux distribution, MCC Interim Linux, in February 1992. A distribution was a complete package that included the Linux kernel, along with the GNU tools and other software needed to create a functional operating system. This was crucial because while Linus was focused on developing the kernel, most users needed a complete system that they could install and use without having to compile everything from source code. The concept of Linux distributions would prove to be one of the key factors in the system's success. Different distributions could target different user communities and use cases while all sharing the same underlying kernel. This allowed for specialization and innovation while maintaining compatibility and avoiding fragmentation. By the end of 1991, Linux had grown from a hobby project into a genuine alternative to commercial operating systems. Version 0.1 was released in October, and version 0.11 followed in December. Each release brought significant improvements and new features, and the community of users and developers continued to expand rapidly. The timing of Linux's emergence was fortuitous. The personal computer industry was experiencing explosive growth, and there was increasing demand for powerful, flexible operating systems that could take advantage of improving hardware. Unix systems remained expensive and complex, while DOS was showing its age and limitations. Linux offered a third path, a Unix-like system that was both free and accessible to individual users and small organizations. In 1992, there was a pivotal moment in transforming Linux from an interesting hobby project into a serious operating system that could compete with commercial alternatives. Linus had established a development model that was revolutionary in its openness and collaborative nature, but the true test would be whether this approach could scale to handle the complexity of a full-featured operating system. The release of Linux version 0.12 in January 1992 marked a crucial milestone. This was the first version to be released under the GNU General Public License, a decision that would have profound implications for the future of the project. Linus had initially released Linux under a license that prohibited commercial distribution, but he came to realize that this restriction was actually hindering the system's adoption and development. The choice to adopt the GPL was not made lightly. Richard Stallman's copyleft license was designed to ensure that any improvements to GPL licensed software would also be freely available, creating what Stallman called a viral effect that would gradually expand the realm of free software. Some developers worried that the GPL's requirements were too restrictive, particularly the clause requiring that derivative works also be released under the GPL. However, Linus recognized that the GPL's philosophy aligned well with his vision for Linux development. The license would prevent any single company from taking Linux proprietary, while ensuring that all improvements would benefit the entire community. This decision attracted many developers who had been working on GNU project components and were looking for a kernel that shared their commitment to software freedom. The technical development of Linux during 1992 was remarkable for its pace and scope. Linus was receiving contributions from dozens of developers around the world, each working on different aspects of the system. The kernel was growing rapidly in both size and capability, adding support for new hardware devices, file systems, and networking protocols. One of the most significant developments was the port of the X Window system to Linux. X was the standard graphical interface for Unix systems, and its availability on Linux was crucial for attracting users who needed more than a command-line interface. The export was led by Orest Zborowski and others, and it demonstrated that Linux could support the same sophisticated applications that ran on expensive Unix workstations. The networking capabilities of Linux also expanded dramatically during this period. Support for TCP/IP, the protocol suite that powers the Internet, was added to the kernel, making Linux a viable platform for network servers and Internet-connected systems. This timing was particularly fortuitous, as the Internet was beginning its transformation from an academic network into a commercial medium that would reshape the global economy. The emergence of Linux distributions continued to accelerate throughout 1992, following H.J. Liu's MCC Interim Linux. Several other distributions appeared, each with its own approach to packaging and installing Linux. The Soft Landing Linux System, or SLS, became one of the most popular early distributions, providing a relatively easy way for users to install a complete Linux system without having to compile everything from source. Patrick Volkerding, a computer science student at Morehead State University, became frustrated with bugs in SLS and decided to create his own distribution. In July 1993, he released the first version of Slackware Linux, which would become one of the longest-running Linux distributions. Slackware emphasized simplicity and stability, following a philosophy that users should understand their system rather than having it hidden behind layers of abstraction. Meanwhile, Ian Murdoch was beginning work on what would become the Debian distribution. Murdoch was strongly influenced by the GNU project's emphasis on free software, and he wanted to create a distribution that would embody these principles. The Debian social contract, first articulated in 1997 but reflecting ideas that Murdoch held from the beginning, committed the project to remaining entirely free and to serving the broader free software community. The proliferation of distributions reflected one of Linux's greatest strengths, its modularity and flexibility. Unlike monolithic commercial operating systems, Linux could be assembled in countless different ways to serve different needs and preferences. This diversity sometimes created confusion for new users, but it also fostered innovation and prevented any single entity from controlling the platform's direction. Commercial interest in Linux began to emerge during 1993 as companies recognized the potential of a free, Unix-like operating system. Yggdrasil Computing was one of the first companies to commercialize Linux, selling CD-ROM distributions and providing support services. This marked the beginning of what would become a thriving ecosystem of companies built around free software. The development community itself was evolving and growing more sophisticated. Linus had established himself as the benevolent dictator of the Linux kernel, making final decisions about what code would be accepted into the official releases. However, he was careful to delegate authority to trusted developers who became maintainers of specific subsystems. This hierarchical structure allowed the project to scale while maintaining technical coherence. Communication within the Linux community relied heavily on mailing lists and Usenet newsgroups. The Linux kernel mailing list became the primary forum for technical discussions about kernel development, while various distribution-specific lists handled user support and distribution development. This electronic communication was essential for coordinating the work of developers scattered around the globe. The culture that emerged around Linux development was distinctive and influential. It emphasized technical merit over credentials, collaboration over competition, and openness over secrecy. Disputes were resolved through technical arguments and working code, rather than corporate politics or appeals to authority. This meritocratic culture attracted many of the brightest programmers in the world, who were drawn to the opportunity to work on cutting-edge technology while contributing to a cause larger than themselves. Version 1 of the Linux kernel was released on March 14, 1994, marking a symbolic milestone in the project's development. The version number change reflected the community's growing confidence that Linux was ready for serious use, though in many ways the kernel was already being used in production environments by adventurous system administrators and organizations. The release of Linux 1 coincided with the emergence of the World Wide Web as a major force in computing. The web's rapid growth created enormous demand for server systems that could handle HTTP requests and serve web pages to browsers around the world. Linux, with its robust networking capabilities and low cost, was perfectly positioned to meet this demand. Many of the early web servers ran on Linux systems, taking advantage of the platform's stability and the availability of free web server software like Apache. This created a virtuous cycle where Linux's adoption drove improvements in its networking and server capabilities, which in turn made it even more attractive for Internet applications. The academic community played a crucial role in Linux's early development and adoption. Universities around the world began using Linux in their computer science programs, both as a teaching tool and as a research platform. Students who learned Linux in college often became advocates for its adoption in their subsequent careers, helping to spread the platform throughout the technology industry. Research institutions were particularly attracted to Linux because it allowed them to modify the operating system to support their specific needs. This was impossible with proprietary systems, where source code was unavailable and modifications were prohibited by licensing agreements. The ability to customize Linux at the kernel level made it an ideal platform for systems research and experimental computing projects. The media began to take notice of Linux during this period, with articles appearing in computer magazines and technical publications. These articles often focused on the unusual development model and the philosophical implications of free software, but they also helped to raise awareness of Linux among a broader audience of computer professionals. One of the most significant early media treatments was an article by Peter Salus in the March 1994 issue of Unix Review, which described Linux as the most important development in the Unix world in years. Such recognition from respected industry publications helped to legitimize Linux in the eyes of conservative IT managers who might otherwise have dismissed it as a student project. The growing success of Linux also attracted criticism from established players in the computing industry. Microsoft, in particular, began to view Linux as a potential threat to its dominance in the operating system market. However, most industry observers still considered Linux to be a niche product, suitable only for technical users and specialized applications. This perception would prove to be dramatically wrong, but it reflected the conventional wisdom of the mid-1990s. Commercial software companies had dominated the industry for so long that many people found it difficult to imagine how a project developed by volunteers could compete with well-funded corporate development teams. The reality was that the open-source development model had several inherent advantages that were not immediately apparent to outside observers. The ability to attract contributors from around the world created a talent pool that no single company could match. The transparency of the development process meant that bugs were found and fixed more quickly than in closed-source projects, and the lack of commercial pressures allowed developers to focus on technical excellence rather than artificial deadlines or marketing requirements. By 1995, Linux had established itself as more than just an academic curiosity or hacker's plaything. The platform was beginning to attract serious attention from corporations, government agencies, and forward-thinking IT departments who recognized its potential for mission-critical applications. The convergence of several technological and economic trends would make the mid to late 1990s a period of explosive growth for Linux and the broader open-source movement. The Internet boom was perhaps the most significant factor driving Linux adoption during this period. The World Wide Web was transforming from a research tool into a commercial medium, and companies around the world were scrambling to establish an online presence. Traditional Unix systems were prohibitively expensive for many organizations, while Windows lacked the stability and networking capabilities needed for serious server applications. Linux offered a compelling third option: enterprise-grade capabilities at a fraction of the cost. Red Hat Software, founded by Bob Young and Mark Ewing in 1993, emerged as one of the most successful companies built around Linux. Red Hat Linux, first released in 1994, pioneered the use of the RPM package management system, which made it much easier to install and manage software on Linux systems. The company's business model was revolutionary. They gave away their software for free but charged for support, training, and consulting services. This approach challenged conventional wisdom about the software industry, which held that companies needed to control and license their intellectual property to generate revenue. Red Hat demonstrated that it was possible to build a profitable business around free software by focusing on services rather than licensing fees. Their success would inspire countless other companies to adopt similar models in the years to come. The development of the Apache web server project paralleled and complemented the growth of Linux during this period. Apache was created by a group of webmasters who wanted to improve upon the National Center for Supercomputing Applications HTTPD server. Like Linux, Apache was developed through an open, collaborative process and released under a free software license. The combination of Linux and Apache proved to be incredibly powerful for web hosting applications. By 1996, Apache was serving more web pages than any other server software, including commercial alternatives from established companies like Netscape and Microsoft. The Apache Software Foundation, established to oversee the project's development, became a model for how open-source projects could be organized and governed. The success of Apache provided additional validation for the open-source development model and helped to establish what would become known as the LAMP stack: Linux, Apache, MySQL, and PHP, or Perl. The release of Linux kernel version 2 in June 1996 marked another major milestone in the platform's evolution. This version included support for multiple processors, improved networking capabilities, and better memory management. The ability to run on multi-processor systems was particularly significant, as it allowed Linux to compete directly with high-end Unix workstations and servers that cost tens of thousands of dollars. Linus Torvalds had proven to be not just a talented programmer, but also an effective leader of a large distributed development team. His approach to project management was deliberately informal and consensus-based, but he maintained firm control over the kernel's architecture and design philosophy. He coined the phrase "release early, release often" to describe his development methodology, which emphasized rapid iteration and community feedback over extensive internal testing. This approach was formalized by Eric Raymond in his influential essay, The Cathedral and the Bazaar, first presented at the Linux Congress in May 1997. Raymond contrasted the traditional cathedral model of software development, where code was carefully crafted by small teams in isolation, with the bazaar model, exemplified by Linux, where development took place in the open with contributions from hundreds of developers. Raymond's essay articulated what many in the Linux community had intuitively understood, that the open-source development model had fundamental advantages over proprietary alternatives. His famous observation that, given enough eyeballs, all bugs are shallow, captured the essence of why distributed development could be more effective than traditional approaches. The essay became required reading for anyone interested in understanding the open-source phenomenon. The corporate world was beginning to take notice of these developments. IBM, historically one of the most conservative companies in the technology industry, began to show interest in Linux as early as 1996. Big Blue's mainframe division was particularly intrigued by the possibility of running Linux on their system, 390 computers, which could potentially breathe new life into the mainframe market. However, it was Oracle Corporation that made the first major corporate endorsement of Linux. In September 1998, Oracle CEO Larry Ellison announced that his company would support Linux as a platform for their database software. This was a watershed moment, as Oracle was one of the most important enterprise software companies in the world. Their endorsement gave Linux credibility in corporate environments, where open-source software had previously been viewed with suspicion. The late 1990s also saw the emergence of several new Linux distributions that would play important roles in the platform's future development. SUSE Linux, originally based on Slackware, was founded in Germany in 1992 but gained international prominence during this period. Caldera, founded by Ray Norder, the former CEO of Novell, aimed to create a business-focused Linux distribution that would appeal to corporate users. Perhaps most significantly, the Debian project was maturing into one of the most technically sophisticated Linux distributions. Debian's commitment to free software principles and its rigorous quality assurance processes made it a favorite among developers and system administrators who prioritized stability and security over ease of use. The Debian Social Contract and Debian Free Software Guidelines became influential documents that helped to define what it meant for software to be truly free. The growth of the Linux community during this period was remarkable, not just in terms of numbers, but also in terms of geographic and cultural diversity. Developers from every continent were contributing to Linux projects, and local user groups were forming in cities around the world. The annual Linux conventions, such as the Linux Expo and Linux World, became important gathering places where community members could meet face-to-face and coordinate their efforts. Educational institutions continued to play a crucial role in Linux adoption. Computer science departments at universities around the world were incorporating Linux into their curricula, both as a subject of study and as a platform for teaching operating systems concepts. Students who learned Linux in college often became advocates for its adoption in their subsequent careers, creating a pipeline of skilled Linux professionals entering the workforce. The embedded systems market was another area where Linux began to gain traction during the late 1990s. The kernel's modular architecture and small footprint made it attractive for specialized applications where traditional desktop operating systems were too bloated or expensive. Companies began using Linux in everything from network routers to industrial control systems, creating new markets for Linux expertise and support. Government agencies also began to show interest in Linux, attracted by both its cost savings and its transparency. The ability to audit the source code was particularly appealing to security-conscious organizations that needed to ensure their systems were free from backdoors or other vulnerabilities. Several European governments initiated studies of open-source software as an alternative to expensive proprietary systems from American companies. The mainstream computer press began to cover Linux more extensively during this period, with articles appearing in publications like PC Week, InfoWorld, and Computer World. These articles often focused on the economic implications of free software, but they also helped to educate IT managers about Linux's technical capabilities. The coverage was not always positive, with some critics questioning whether volunteer-developed software could be reliable enough for business-critical applications. Microsoft began to take Linux seriously as a competitive threat during this period. Internal company documents, later revealed during the antitrust trial, showed that Microsoft executives were concerned about the growing popularity of open-source software. The company began what it called a Linux strategy, aimed at countering the threat posed by free alternatives to Windows. The Halloween documents, leaked Microsoft memos published by Eric Raymond in late 1998, revealed the company's internal assessment of the open-source threat. The documents acknowledged that open-source software could match or exceed the quality of proprietary alternatives while offering significant cost advantages. Microsoft's response strategy included embracing and extending open standards, improving Windows reliability, and attacking open source through marketing and legal channels. The late 1990s also saw the beginning of the dot-com boom, which would have profound implications for Linux adoption. Internet startups, many of them funded by venture capital, needed to build their infrastructure quickly and cheaply. Linux offered an ideal platform for these companies, providing enterprise-grade capabilities without the licensing costs associated with proprietary alternatives. Companies like Amazon, Google, and Yahoo built their entire infrastructures on Linux-based systems, demonstrating that open-source software could scale to handle massive workloads. These success stories helped to further legitimize Linux in the eyes of traditional businesses that were considering adopting open-source solutions. The mid-2000s marked a period of maturation and mainstream acceptance for Linux, as the platform evolved from a disruptive technology into an essential component of the global computing infrastructure. The release of Linux kernel version 2.6 in December 2003 introduced fundamental architectural improvements that would serve as the foundation for the next decade of development. This version included a completely rewritten process scheduler, improved support for symmetric multiprocessing, and better real-time capabilities. The new scheduler, developed by Ingo Molnar, was particularly significant because it dramatically improved Linux's performance on desktop systems. Previous versions of Linux had been optimized primarily for server workloads, where throughput was more important than responsiveness. The 2.6 kernel's O1 scheduler ensured that interactive applications would remain responsive even under heavy system load, making Linux a more viable option for desktop users. Ubuntu's release in October 2004 represented a watershed moment for Linux desktop adoption. Mark Shuttleworth's vision of a Linux distribution that was as polished and user-friendly as commercial alternatives began to take shape with Ubuntu 4.1, codenamed Warty Warthog. The distribution's focus on ease of installation, hardware detection, and out-of-the-box functionality addressed many of the usability issues that had historically prevented mainstream adoption of Linux on desktop systems. Shuttleworth's approach was revolutionary in several ways. Unlike most Linux distributions, which were developed primarily by volunteers, Ubuntu was backed by Shuttleworth's personal fortune and operated through his company, Canonical. This funding allowed the project to hire full-time developers and designers who could focus on polishing the user experience rather than just adding new features. The Ubuntu philosophy of Linux for human beings emphasized accessibility and inclusivity. The distribution included extensive internationalization support, accessibility features for users with disabilities, and documentation written for non-technical users. The Ship It program, which allowed users to order free Ubuntu CDs by mail, helped to spread the distribution to parts of the world where high-speed internet access was not readily available. Meanwhile, the enterprise adoption of Linux continued to accelerate. Oracle's acquisition of SleepyCat Software in 2006, the makers of Berkeley DB, demonstrated the growing importance of open-source components in commercial software stacks. Larry Ellison's company was not just endorsing Linux, but actively acquiring open-source companies to expand their product portfolio. The virtualization revolution that had begun in the early 2000s reached new heights with the release of Zen 3 in 2005. This version introduced support for running unmodified operating systems as guest machines, making it much easier for organizations to migrate existing workloads to virtualized environments. The combination of Linux and Zen provided a compelling alternative to expensive proprietary virtualization solutions from companies like VMware. Amazon Web Services, launched in 2006, would prove to be one of the most important developments in the history of computing, and Linux played a central role in making it possible. Amazon's Elastic Compute Cloud (EC2) service allowed users to rent virtual servers on demand, paying only for the computing resources they actually used. The vast majority of EC2 instances ran Linux, making Amazon one of the largest Linux deployment environments in the world. The success of AWS demonstrated the power of the infrastructure as a service model and helped to popularize what would later become known as cloud computing. For Linux, this represented a massive new market opportunity, as cloud providers needed operating systems that were reliable, scalable, and cost-effective. Proprietary operating systems with per-seat licensing fees were economically unfeasible at the scale required by cloud computing. Google's influence on the Linux ecosystem also grew dramatically during this period. The company's massive data centers, which processed billions of search queries and served web pages to users around the world, ran almost entirely on Linux systems. Google's engineering teams made significant contributions to kernel development, particularly in areas related to networking, file systems, and power management. The emergence of the Android operating system, announced by Google in November 2007, would eventually become one of the most important Linux-based platforms in history. While Android was built on the Linux kernel, it represented a radical departure from traditional Linux distributions. The Android software stack included a Java-based application framework and a custom user interface designed specifically for mobile devices. Initially, the relationship between Android and the broader Linux community was somewhat strained. Google had made significant modifications to the kernel that were not accepted into the mainline Linux tree, creating what some developers called a fork of Linux. However, over time, many of these changes were merged back into the main kernel, and Android became an important driver of Linux development in areas like power management and real-time performance. The late 2000s also saw the emergence of several new Linux distributions that would play important roles in the platform's future development. CentOS, a community-supported rebuild of Red Hat Enterprise Linux, provided organizations with access to enterprise-grade Linux without the subscription costs. The project demonstrated how the open source model could create competitive alternatives even to commercial Linux distributions. Fedora, which had emerged from Red Hat's decision to split their product line into community and commercial editions, became an important testing ground for new technologies that would eventually make their way into Red Hat Enterprise Linux. The Fedora project's leading-edge philosophy meant that it often included the latest versions of software, packages, and kernel features, making it popular among developers and early adopters. The desktop Linux market also saw significant developments during this period. The launch of the One Laptop Per Child project in 2005, led by MIT's Nicholas Negroponte, aimed to provide low-cost computers to children in developing countries. The EXO laptop, which ran a custom Linux-based operating system, demonstrated that open-source software could enable new approaches to computing and education. While the OLPC project faced numerous challenges and never achieved its ambitious goals for global deployment, it highlighted the potential for Linux to enable computing in environments where traditional commercial software would be too expensive or inappropriate. The project's influence could be seen in the later development of netbooks and tablet computers, many of which used Linux-based operating systems. The development of solid-state drives during this period also had important implications for Linux adoption. SSDs offered significant performance advantages over traditional hard drives, but they also required changes to operating system design to take full advantage of their capabilities. Linux kernel developers were among the first to implement optimizations for SSD storage, giving Linux-based systems a competitive advantage in high-performance applications. Version control systems also underwent a revolution during this period, with significant implications for open-source development. Linus Torvalds, frustrated with the limitations of existing version control tools, created Git in 2005 to manage Linux kernel development. Git's distributed architecture and powerful merging capabilities made it much easier to coordinate the work of hundreds of developers across multiple time zones and organizations. The creation of Git had implications far beyond Linux kernel development. The tool's success helped to popularize distributed version control and influence the development of platforms like GitHub, which would later become essential infrastructure for open-source projects. Git's design philosophy, which emphasized speed, simplicity, and support for distributed development, reflected many of the same principles that had made Linux successful. The economic crisis of 2008 created both challenges and opportunities for Linux adoption. Many organizations facing budget constraints began to look more seriously at open-source alternatives to expensive proprietary software. The total cost of ownership advantages of Linux became more compelling when companies were under pressure to reduce their IT spending. At the same time, the crisis demonstrated the importance of vendor independence and avoiding lock-in to proprietary platforms. Organizations that had built their infrastructure around open-source technologies were better positioned to adapt to changing economic conditions because they were not dependent on the financial stability or strategic decisions of a single vendor. The netbook phenomenon, which peaked in the late 2000s, provided another important validation of Linux's capabilities in consumer markets. These small, inexpensive laptops were designed primarily for web browsing and basic productivity tasks, making them ideal candidates for Linux-based operating systems. ASUS, the company that popularized netbooks with their EPC line, initially offered many models with Linux pre-installed. While Windows eventually dominated the netbook market as Microsoft reduced licensing fees and hardware capabilities improved, the initial success of Linux-based netbooks demonstrated that consumers were willing to use alternative operating systems when they provided clear value propositions. This experience would prove valuable as the industry moved toward tablets and smartphones, where Linux-based Android would eventually achieve dominant market share. The 2010s would prove to be a transformative decade for Linux, as the platform became the invisible foundation supporting the digital revolution that was reshaping every aspect of human society. The proliferation of smartphones, the explosion of cloud computing, and the emergence of new technologies like containers and orchestration would create unprecedented demand for Linux-based systems. The mobile revolution began in earnest with the release of the first Android smartphones in 2008, but it reached critical mass in the early 2010s. By 2011, Android had become the world's most popular smartphone operating system, surpassing even Apple's iOS in market share. This achievement was remarkable considering that Android had been in development for less than 5 years and was competing against established players with decades of mobile experience. Android's success validated many of the core principles that had made Linux successful in other markets. The open-source development model allowed multiple hardware manufacturers to adopt and customize the platform, creating a diverse ecosystem of devices at different price points. Companies like Samsung, HTC, and Motorola could differentiate their products while sharing the costs of operating system development across the entire Android ecosystem. However, Android's relationship with the traditional Linux community remained complex. Google had made significant modifications to the Linux kernel to support mobile-specific requirements like aggressive power management and real-time graphics performance. These changes, known as Androidisms, were initially rejected by the mainline kernel maintainers, creating a situation where Android devices ran a forked version of Linux that diverged significantly from other Linux distributions. The fragmentation between Android and mainline Linux created technical and philosophical challenges for the broader Linux community. Some developers worried that Android's success would lead to a proliferation of incompatible Linux variants, undermining the platform's unity and compatibility. Others argued that Android's innovations, particularly in power management and user interface design, could benefit all Linux users if properly integrated into the mainline kernel. The containerization revolution that began in the early 2010s represented another major milestone in Linux's evolution. While container technology had existed in various forms for decades, the release of Docker in 2013 made containers accessible to mainstream developers and system administrators. Docker's ease of use and powerful packaging model democratized container technology in much the same way that early Linux distributions had democratized Unix. Containers offered several advantages over traditional virtualization approaches. They were more lightweight than virtual machines, allowing organizations to achieve higher density on their hardware. They also provided better consistency between development and production environments, addressing the perennial problem of software that worked on a developer's laptop but failed in production. The container ecosystem that emerged around Docker was built almost entirely on Linux technologies. The Linux kernel's control groups and namespaces provided the isolation mechanisms that made containers possible, while Linux distributions served as the base images for most container deployments. Windows containers would eventually be developed, but Linux remained the dominant platform for containerized applications. The rise of DevOps practices during this period also played to Linux's strengths. The DevOps movement emphasized automation, collaboration between development and operations teams, and rapid deployment cycles. Linux's command line interface, powerful scripting capabilities, and extensive automation tools made it an ideal platform for implementing DevOps workflows. Infrastructure as code, one of the key concepts in DevOps, relied heavily on Linux-based tools and platforms. Configuration management systems like Puppet, Chef, and Ansible were designed primarily for Linux environments, though they eventually gained support for other platforms. The ability to version control and programmatically manage infrastructure configurations was particularly valuable in cloud environments where resources were ephemeral and manually configured systems were impractical. The emergence of Kubernetes in 2014 represented the next evolution in container orchestration and cluster management. Originally developed by Google based on their internal Borg system, Kubernetes provided a sophisticated platform for managing containerized applications at scale. The project was donated to the Cloud Native Computing Foundation ensuring that it would remain open source and vendor neutral. Kubernetes became one of the most important open source projects of the decade, attracting contributions from companies across the technology industry. The platform's success demonstrated that complex distributed systems could be successfully developed through open source collaboration, even when the challenges involved were far more sophisticated than those faced by earlier open source projects. The public cloud market continued its explosive growth throughout the 2010s, with Amazon Web Services maintaining its leadership position while facing increasing competition from Microsoft Azure and Google Cloud Platform. All three major cloud providers built their infrastructure primarily on Linux systems, making cloud computing one of the largest drivers of Linux adoption in history. The economies of scale achieved by cloud providers created unprecedented demand for efficient, reliable operating systems. Traditional licensing models based on per-seat fees became economically unfeasible when applied to the millions of virtual machines running in cloud data centers. Linux's combination of performance, reliability, and zero licensing costs made it the obvious choice for cloud infrastructure. The software-defined networking revolution that accompanied cloud computing also relied heavily on Linux technologies. Open vSwitch, originally developed at Nicira and later acquired by VMware, provided the virtual networking capabilities needed to create flexible, programmable network infrastructures. The Linux kernel's networking stack was extensively enhanced to support these new use cases, with improvements in areas like network namespaces, traffic shaping, and high-performance packet processing. Edge computing emerged as another important trend during the late 2010s, driven by the need to process data closer to its source and reduce latency for real-time applications. The Internet of Things was generating massive amounts of data that needed to be processed and analyzed, but sending all of this data to centralized cloud data centers was often impractical due to bandwidth and latency constraints. Linux's flexibility and efficiency made it an ideal platform for edge computing deployments. The kernel could be customized and optimized for specific hardware platforms and use cases, while maintaining compatibility with standard Linux applications and development tools. Projects like Yocto and OpenWRT provided specialized Linux distributions designed for embedded and edge computing applications. The security landscape also evolved significantly during the 2010s, with new threats and attack vectors emerging as computing became more distributed and interconnected. The Linux community responded with innovations like the Linux Security Modules framework, which provided a standardized way to implement mandatory access controls and other security enhancements. SE Linux, originally developed by the National Security Agency, became an important component of enterprise Linux distributions, providing fine-grained access controls that could prevent many types of security breaches. AppArmor, developed by Novell, offered an alternative approach to application security that was easier to configure but somewhat less powerful than SE Linux. The Heartbleed vulnerability, discovered in the OpenSSL library in 2014, highlighted both the challenges and strengths of open-source security. The vulnerability had existed for several years before being discovered, demonstrating that the many eyeballs principle did not guarantee rapid detection of all security flaws. However, the response to Heartbleed also showed the benefits of open-source development, as fixes were developed and deployed more rapidly than would have been possible with proprietary software. The emergence of artificial intelligence and machine learning as mainstream technologies during the late 2010s created new opportunities for Linux adoption. The computational requirements of training and deploying machine learning models made GPUs and specialized hardware increasingly important, and Linux provided better support for these platforms than most alternative operating systems. TensorFlow, Google's open-source machine learning framework, was designed primarily for Linux environments, though it eventually gained support for other platforms. The combination of Linux, powerful hardware, and sophisticated machine learning frameworks enabled researchers and companies to tackle problems that had previously been considered unsolvable. The container orchestration ecosystem continued to evolve throughout the decade, with technologies like Service Mesh emerging to address the challenges of managing communication between microservices. Istio, developed by Google, IBM, and Lyft, provided sophisticated traffic management, security, and observability features for containerized applications running on Kubernetes. The rise of serverless computing, exemplified by AWS Lambda and similar offerings from other cloud providers, represented another evolution in how applications were deployed and managed. While serverless platforms abstracted away much of the underlying infrastructure, they were typically built on Linux-based systems and relied on container technologies for isolation and resource management. The gaming industry also began to show increased interest in Linux during this period. Valve Corporation's Steam platform added support for Linux in 2012, bringing thousands of commercial games to the platform for the first time. While Linux remained a small fraction of the gaming market, the availability of popular games helped to attract users who had previously been reluctant to abandon Windows. The Raspberry Pi, released in 2012, democratized access to Linux computing and introduced a new generation of users to open-source software. The credit card-sized computer, originally designed to teach programming to children, became popular with hobbyists, educators, and professionals who needed an inexpensive, versatile computing platform. The success of the Raspberry Pi demonstrated that there was significant demand for accessible, affordable computing devices that could run full Linux distributions. The project inspired numerous similar single-board computers and helped to establish Linux as the dominant platform for maker communities and educational computing. As the 2010s drew to a close and the 2020s began, Linux had evolved far beyond its origins as a hobbyist operating system to become the bedrock of modern digital infrastructure. The platform's influence extended into virtually every aspect of computing, from the smartphones in people's pockets to the massive data centers powering the global internet. However, new challenges and opportunities were emerging that would test Linux's adaptability and relevance in an increasingly complex technological landscape. The advent of edge computing represented a fundamental shift in how computational resources were distributed and utilized. Rather than centralizing processing in massive cloud data centers, organizations were pushing computing power closer to where data was generated and consumed. This trend was driven by several factors: the explosive growth of Internet of Things devices, the need for real-time processing in applications like autonomous vehicles, and concerns about latency and bandwidth consumption. Linux's modular architecture and lightweight resource requirements made it ideally suited for edge computing deployments. Industrial IoT systems, smart city infrastructure, and autonomous vehicle platforms increasingly relied on Linux-based controllers and gateways. The kernel's real-time capabilities, enhanced through projects like the RT-Premt patch set, enabled Linux to meet the strict timing requirements of safety-critical applications. The automotive industry's embrace of Linux represented a particularly significant development. The automotive-grade Linux project, launched by the Linux Foundation in 2012, brought together automakers, suppliers, and technology companies to develop an open-source platform for connected vehicles. By the late 2010s, Linux was running in everything from infotainment systems to advanced driver assistance systems, with major manufacturers like Toyota, Mercedes-Benz, and Ford committing to Linux-based platforms. The complexity of modern vehicles, which contained hundreds of electronic control units and millions of lines of code, made traditional proprietary development approaches increasingly untenable. The automotive industry's adoption of Linux reflected broader trends towards software-defined vehicles and the need for platforms that could support rapid innovation and over-the-air updates. Quantum computing emerged as another frontier where Linux was establishing an early presence. While quantum computers operated on fundamentally different principles than classical computers, they still required sophisticated control software to manage quantum gates, error correction, and communication with classical computing systems. IBM's Qiskit framework, Google's Cirq platform, and other quantum development tools were built primarily for Linux environments. The intersection of quantum and classical computing represented a new challenge for operating system design. Quantum computers required extremely precise timing and control, while also needing to interface with classical systems for programming, monitoring, and result processing. Linux's flexibility and real-time capabilities positioned it well to serve as the bridge between these two computing paradigms. The container ecosystem continued to evolve throughout the late 2010s and early 2020s, with new technologies addressing the challenges of security, networking, and storage in containerized environments. The Open Container Initiative, established in 2015, provided standardization for container formats and runtimes, ensuring interoperability between different container platforms while preventing fragmentation. Podman, developed by Red Hat as an alternative to Docker, introduced new concepts like rootless containers and daemonless operation that addressed some of the security and architectural concerns with earlier container technologies. The ability to run containers without requiring root privileges significantly improved security for development and testing environments, while the daemonless architecture reduced complexity and potential points of failure. The rise of WebAssembly as a portable compilation target created new possibilities for running applications across different platforms and environments. While WebAssembly was initially designed for web browsers, it quickly found applications in server-side computing, edge computing, and even embedded systems. Linux distributions began including WebAssembly runtimes, and projects like Wasmtime and Wasm provided sophisticated execution environments for WebAssembly modules. The COVID-19 pandemic, which began in late 2019, had profound implications for technology adoption and Linux deployment. The sudden shift to remote work created unprecedented demand for cloud computing, video conferencing, and collaboration tools. Organizations that had been hesitant to embrace cloud technologies found themselves forced to migrate quickly to support distributed workforces. This acceleration of digital transformation benefited Linux in several ways. Cloud providers experienced massive growth in demand, requiring rapid expansion of their Linux-based infrastructure. The increased focus on cost optimization made Linux's zero licensing fees more attractive to organizations facing economic uncertainty. And the emphasis on automation and infrastructure as code played to Linux's strengths in programmable infrastructure management. The supply chain disruptions caused by the pandemic also highlighted the risks of depending on proprietary software from single vendors. Organizations began placing greater emphasis on vendor independence and the ability to modify and customize their software stack. Open source alternatives became more attractive, not just for their cost benefits, but also for their strategic advantages in terms of flexibility and vendor independence. The emergence of artificial intelligence and machine learning as transformative technologies continued to drive Linux adoption throughout this period. The computational requirements of training large neural networks made GPUs and specialized AI accelerators essential, and Linux provided the best support for these platforms. MLOps, the practice of applying DevOps principles to machine learning workflows, relied heavily on Linux-based tools and platforms. Kubernetes became the de facto standard for orchestrating machine learning workloads, with specialized projects like Kubeflow providing ML-specific capabilities on top of the core Kubernetes platform. The ability to scale machine learning training and inference across clusters of hundreds or thousands of nodes was only practical with sophisticated orchestration platforms, and these platforms were built almost exclusively on Linux. The growing importance of data, privacy, and sovereignty created new requirements for Linux deployments. Regulations like the European Union's General Data Protection Regulation, GDPR, and various national data localization laws required organizations to have fine-grained control over where their data was processed, stored. Linux's transparency and customizability made it easier for organizations to implement the technical controls needed to comply with these regulations. Confidential computing, which aimed to protect data while it was being processed, relied heavily on Linux-based platforms. Technologies like Intel's Software Guard extensions, SGX, and AMD's Secure Encrypted Virtualization, SEV, provided hardware-based protection for sensitive workloads, but they required operating system support to be effective. Linux kernel developers worked closely with hardware vendors to implement support for these technologies. The rise of 5G networks created new opportunities and challenges for Linux deployments. The low latency and high bandwidth capabilities of 5G enabled new classes of applications, from augmented reality to real-time industrial automation. However, these applications also required computing infrastructure to be deployed closer to the network edge, creating demand for Linux systems that could operate reliably in challenging environments. Network Functions Virtualization, NFV, and Software-Defined Networking, SDN, transformed the telecommunications industry, replacing dedicated hardware appliances with software running on commodity servers. This transformation was built almost entirely on Linux platforms, with projects like OpenStack providing the infrastructure management capabilities needed for telecom-grade deployments. The container-native storage ecosystem also matured during this period, with projects like Ceph, GlusterFS, and newer solutions like Rook providing distributed storage capabilities for containerized applications. The ephemeral nature of containers created new challenges for data persistence and backup, requiring storage solutions that could automatically provision and manage storage resources across cluster deployments. The serverless computing model continued to evolve, with new platforms like Knative providing Kubernetes-native serverless capabilities. The ability to automatically scale applications from 0 to thousands of instances based on demand required sophisticated scheduling and resource management capabilities that were only possible on platforms like Linux with advanced container and networking support. Security remained a critical concern throughout this period, with new attack vectors emerging as applications became more distributed and interconnected. The concept of zero-trust networking, which assumed that no component of a system could be implicitly trusted, required fine-grained access controls and continuous monitoring. Linux's mature security subsystems, including SELinux, AppArmor, and the growing ecosystem of security-focused container technologies, provided the foundation for implementing zero-trust architectures. The software supply chain security became an increasingly important concern following high-profile attacks like the SolarWinds compromise. Organizations began implementing more rigorous processes for verifying the integrity and provenance of their software dependencies. Linux distributions enhanced their package signing and verification processes, while new projects like Sigstore provided infrastructure for signing and verifying software artifacts. The rise of GitOps, which extended the infrastructure as code concept to include application deployment and management, relied heavily on Git and Kubernetes, both of which were Linux-native technologies. The ability to manage entire application lifecycles through version-controlled configuration files provided new levels of reproducibility and auditability for complex distributed systems. Open-source business models continued to evolve during this period, with new approaches emerging to balance the needs of sustainable development with the principles of software freedom. The concept of open core became more common, where companies provided a basic open-source platform while offering commercial extensions and support services. This model allowed companies to fund open-source development while still building profitable businesses around their projects. The middle years of the 2020s marked a period of unprecedented innovation and consolidation for Linux, as the platform adapted to emerging technologies that would define the next generation of computing. Artificial intelligence had moved beyond experimental applications to become a fundamental driver of business value, and scientific discovery, creating new demands for computational infrastructure that only Linux's flexibility and scalability could satisfy. The advent of large language models and generative AI represented a paradigm shift in how humans interacted with computers. Models like GPT-3, released by OpenAI in 2020, demonstrated capabilities that seemed almost magical to users who had grown accustomed to the limitations of traditional software. Training these models required computational resources on a scale that had never before been attempted, with some training runs consuming the equivalent processing power of small countries. Linux became the foundation for this AI revolution, not by accident but by necessity. The distributed nature of AI training, which required coordinating thousands of GPUs across multiple data centers, demanded an operating system that could handle complex networking, precise timing, and massive parallelism. The ability to customize and optimize the kernel for specific workloads gave Linux users significant advantages in the fiercely competitive AI training market. NVIDIA's rise to become one of the world's most valuable companies was inextricably linked to Linux's dominance in AI computing. The company's CUDA platform and specialized AI chips required sophisticated driver support and system integration that Linux provided more effectively than any alternative. The symbiotic relationship between NVIDIA's hardware and Linux's software created a powerful ecosystem that accelerated AI development across the industry. The emergence of foundation models, which could be fine-tuned for specific applications rather than trained from scratch, democratized access to advanced AI capabilities. However, this democratization also created new infrastructure challenges, as organizations needed to deploy and serve these models at scale. Linux's container ecosystem, enhanced with AI-specific optimizations, provided the platform for model-serving infrastructure that could handle millions of inference requests per second. Edge AI became increasingly important as organizations sought to deploy AI capabilities closer to their users and data sources. Privacy concerns, regulatory requirements, and latency constraints drove demand for AI processing that could operate without sending sensitive data to centralized cloud services. Linux's ability to run efficiently on resource-constrained hardware, from embedded processors to edge servers, made it the natural choice for edge AI deployments. The convergence of 5G networks and edge computing created new architectural possibilities that were only practical with Linux-based infrastructure. Multi-access edge computing, MEC, enabled applications to process data within the cellular network infrastructure itself, reducing latency to milliseconds and enabling new classes of real-time applications. Autonomous vehicles, augmented reality, and industrial automation all benefited from this edge processing capability. The hyperscale cloud providers continued to innovate with custom silicon designed specifically for their workloads. Amazon's Graviton processors, Google's Tensor processing units, and Microsoft's custom chips all required deep integration with Linux to achieve optimal performance. The open-source nature of Linux enabled these companies to modify and optimize the operating system for their specific hardware, creating competitive advantages that would have been impossible with proprietary alternatives. Sustainability and energy efficiency became increasingly important considerations for data center operators as the environmental impact of computing came under greater scrutiny. Linux's efficiency advantages, which had always been significant, became even more valuable as organizations sought to reduce their carbon footprints. The ability to optimize the kernel for specific workloads and hardware configurations enabled data centers to achieve better performance per watt than would have been possible with less flexible operating systems. The rise of WebAssembly as a portable execution environment created new possibilities for application deployment and sandboxing. WASM's promise of write once, run anywhere began to be realized not just in web browsers, but in server environments, edge computing platforms, and even embedded systems. Linux distributions began including optimized WebAssembly runtimes, and new projects emerged to provide Kubernetes native WebAssembly execution environments. Blockchain and cryptocurrency technologies, despite their environmental controversies, continued to drive demand for specialized computing infrastructure. The proof-of-work consensus mechanisms used by Bitcoin and other cryptocurrencies required massive parallel computation that was most efficiently deployed on Linux systems. Even as the industry moved toward more energy-efficient proof-of-stake mechanisms, the complex validation and smart contract execution required by blockchain platforms continued to benefit from Linux's flexibility and performance. The concept of the metaverse, popularized by companies like Meta, formerly Facebook, created new requirements for real-time graphics processing, network optimization, and distributed system coordination. While much of the metaverse hype proved to be premature, the underlying technologies for virtual and augmented reality did create genuine demand for high-performance computing infrastructure. Linux's support for advanced graphics hardware and low-latency networking made it an essential platform for metaverse infrastructure. Quantum computing began its transition from research curiosity to practical application during this period. While universal quantum computers remained largely experimental, quantum advantage was demonstrated for specific problem domains like optimization and simulation. Linux served as the control system for most quantum computers, managing the classical computation needed to prepare quantum states, execute quantum algorithms, and process results. The intersection of quantum and classical computing required new approaches to system design and resource management. Hybrid algorithms that combined classical and quantum processing needed operating systems that could coordinate between fundamentally different computational models. Linux's real-time capabilities and flexible scheduling made it well suited for these hybrid workloads. The automotive industry's transformation accelerated throughout the mid-2020s, with electric vehicles becoming mainstream and autonomous driving capabilities improving rapidly. Modern vehicles contained more computing power than early supercomputers, and much of this computation ran on Linux-based systems. Over-the-air updates, which allowed manufacturers to add new features and fix bugs after vehicles were sold, required robust and secure update mechanisms that Linux's package management systems provided. The software-defined vehicle concept extended beyond infotainment and driver assistance to include fundamental vehicle control systems, electric vehicle battery management, adaptive suspension systems, and even steering and braking began to rely on software that needed to meet automotive safety standards while remaining updatable throughout the vehicle's lifetime. Linux's deterministic real-time capabilities and mature safety certification frameworks made it suitable for these safety-critical applications. Space exploration and satellite deployment experienced a renaissance during this period, driven by companies like SpaceX, Blue Origin, and numerous smaller satellite operators. The thousands of satellites launched annually required computing systems that could operate reliably in the harsh environment of space, while remaining cost-effective for mass deployment. Linux's reliability, efficiency, and customizability made it the dominant platform for satellite computing systems. The emergence of satellite internet constellations created new networking challenges and opportunities. Managing communication between thousands of satellites while providing internet access to users around the world required sophisticated network routing and resource management capabilities. Linux's advanced networking stack and container orchestration platforms provided the foundation for these mega-constellation control systems. Industrial automation continued its evolution toward more flexible and intelligent systems. Industry 4 concepts like digital twins, predictive maintenance, and adaptive manufacturing required computing platforms that could integrate with legacy industrial equipment while supporting modern AI and analytics workloads. Linux's support for real-time operation, extensive device driver ecosystem, and container-based application deployment made it ideal for these hybrid industrial environments. The concept of digital sovereignty gained increasing importance as nations sought to reduce their dependence on foreign technology providers. Several countries launched initiatives to develop domestic alternatives to imported software and hardware, with Linux serving as a foundation for these efforts. The transparency and customizability of open-source software made it easier for nations to verify that their critical infrastructure was free from backdoors or other security compromises. European initiatives like Gaia-X and the European Cloud Infrastructure aimed to create sovereign cloud platforms that could compete with American and Chinese providers while ensuring compliance with European regulations and values. These initiatives relied heavily on Linux and other open-source technologies to avoid dependence on proprietary software from potentially hostile nations. The cybersecurity landscape continued to evolve in response to increasingly sophisticated threats. Nation-state actors, criminal organizations, and terrorist groups all demonstrated advanced capabilities for disrupting critical infrastructure and stealing sensitive information. Linux's security architecture, enhanced with technologies like mandatory access controls, hardware-based attestation, and zero-trust networking, provided the foundation for defending against these advanced threats. The concept of security by design became increasingly important as systems became more complex and interconnected. Rather than adding security as an afterthought, new systems were designed from the ground up with security as a primary consideration. Linux's modular architecture and extensive security frameworks made it easier to implement security by design principles compared to monolithic proprietary systems. Container security emerged as a critical discipline as containerized applications became the dominant deployment model for new software. Technologies like gvisor, Kata containers, and Firecracker provided additional isolation between containers and the host system, while service mesh technologies like Istio provided sophisticated network security policies for microservices architectures. The rise of confidential computing accelerated as organizations sought to protect sensitive data even from cloud providers and system administrators. Technologies like Intel's Trust Domain Extensions and AMD's secure encrypted virtualization enabled applications to run in encrypted enclaves that were protected even from privileged access. Linux kernel support for these technologies enabled new deployment models where sensitive workloads could run in public clouds without exposing data to the cloud provider. The late 2020s witnessed Linux's evolution into something far beyond what its original creators had envisioned, a universal computing substrate that powered everything from quantum computers to interplanetary missions. The platform's ability to adapt to radically new computing paradigms while maintaining backward compatibility had proven to be one of its greatest strengths, enabling a seamless transition between technological generations that would have been impossible with more rigid proprietary systems. The maturation of neuromorphic computing represented one of the most significant developments of this period. Unlike traditional von Neumann architectures that separated processing and memory, neuromorphic chips mimicked the structure of biological neural networks, with computation and storage integrated at the device level. Intel's Loihi processors, IBM's True North chips, and similar designs from other manufacturers required operating system support that could manage these fundamentally different computational models. Linux kernel developers rose to this challenge by implementing new scheduling algorithms and memory management techniques specifically designed for neuromorphic workloads. The kernel's modular architecture allowed for the creation of specialized subsystems that could handle the event-driven, asynchronous nature of neuromorphic computation while maintaining compatibility with traditional applications. This flexibility enabled organizations to deploy hybrid systems that combined conventional processors with neuromorphic accelerators for specific workloads. The emergence of programmable matter and molecular computing pushed the boundaries of what constituted a computer system. Research projects exploring DNA-based data storage and protein-based computation required control systems that could interface with biological processes at the molecular level. While these technologies remained largely experimental, Linux's adaptability positioned it well to serve as the bridge between digital and biological computing paradigms. Brain-computer interfaces, BCIs, transitioned from medical research tools to consumer products during this period, creating new requirements for real-time processing of neural signals. The need to process hundreds of channels of brain activity in real time while maintaining strict safety and privacy requirements demanded operating systems with microsecond precision timing and robust security guarantees. Linux's real-time kernel extensions and mandatory access control systems provided the foundation for these safety-critical BCI applications. The deployment of nuclear fusion power plants, which finally became commercially viable in the late 2020s, created new challenges for industrial control systems. Fusion reactors required computing systems that could manage plasma confinement with extraordinary precision while maintaining safety systems that could respond to anomalies within milliseconds. The consequences of software failure in these systems were so severe that only the most thoroughly tested and verified platforms could be considered acceptable. Linux's transparent development process and extensive verification tools made it the preferred platform for fusion control systems. The ability to audit every line of code, combined with formal verification techniques and real-time guarantees, provided the level of assurance required for these critical applications. Multiple independent implementations of safety systems, all based on different Linux configurations, provided defense in depth against both hardware and software failures. The space industry's expansion accelerated dramatically during this period, with permanent bases being established on the Moon and Mars. These extraterrestrial outposts required computing systems that could operate autonomously for months at a time, with communication delays to Earth measured in minutes or hours. The harsh radiation environment and extreme temperature variations of space created additional challenges for both hardware and software systems. Linux's reliability and extensive remote management capabilities made it the natural choice for space computing systems. The ability to update and reconfigure systems remotely while maintaining strict safety guarantees was essential for missions where physical access was impossible. Redundant Linux systems with automatic failover capabilities provided the fault tolerance needed for life support and critical infrastructure systems. The development of interplanetary internet protocols, designed to handle the extreme delays and intermittent connectivity of space communications, relied heavily on Linux networking capabilities. Delay-tolerant networking protocols and store and forward mechanisms required operating system support for managing long-term data queues and sophisticated routing algorithms. Linux's flexible networking stack could be adapted to handle communication delays measured in hours while maintaining compatibility with terrestrial internet protocols. Artificial general intelligence research, while still far from achieving human-level capabilities, began producing systems that could perform multiple cognitive tasks at superhuman levels. These AI systems required computing infrastructure that could handle the massive memory requirements and computational complexity of reasoning across multiple domains simultaneously. Linux's virtual memory system and process scheduling algorithms were enhanced to support AI workloads that could consume terabytes of memory and require coordination across thousands of processing cores. The concept of AI safety became increasingly important as these systems approached and exceeded human performance in specific domains. The ability to monitor, control, and if necessary, shut down AI systems required operating system support for fine-grained resource management and security controls. Linux's mandatory access control systems and container isolation technologies provided the foundation for AI safety mechanisms that could prevent potentially dangerous AI systems from accessing critical resources or communicating inappropriately. Digital biology emerged as a new field that combined biotechnology, with advanced computing to design and control biological systems. CRISPR gene editing systems controlled by Linux computers enabled precise modification of living organisms for medical and industrial applications. Synthetic biology platforms used Linux-based control systems to manage the complex biochemical processes involved in manufacturing everything from pharmaceuticals to biofuels using engineered microorganisms. The convergence of biology and computing created new security challenges that required novel solutions. Biological systems could potentially be hijacked or modified by malicious actors, creating threats that traditional cybersecurity approaches were not designed to handle. Linux's security architecture was extended to include biological threat detection and containment mechanisms, creating what researchers called bio-cybersecurity frameworks. Climate engineering projects, designed to address the ongoing challenges of global warming, relied heavily on Linux-based monitoring and control systems. Atmospheric carbon capture facilities, solar radiation management systems, and ocean alkalinization projects all required sophisticated computing infrastructure to monitor environmental conditions and coordinate global-scale interventions. The distributed nature of these systems, which spanned multiple continents and operated continuously for decades, demanded the reliability and maintainability that Linux provided. The emergence of smart cities as comprehensive urban operating systems represented another domain where Linux's flexibility proved invaluable. Modern cities contained millions of sensors, actuators, and connected devices that needed to be coordinated to optimize everything from traffic flow to energy consumption. Linux-based edge computing platforms distributed throughout urban infrastructure provided the processing power needed to make real-time decisions about city operations. Privacy and digital rights became increasingly important considerations as these smart city systems collected unprecedented amounts of data about citizens' daily activities. Linux's transparent architecture and strong security capabilities enabled cities to implement privacy, preserving analytics that could optimize urban systems without compromising individual privacy. Differential privacy techniques and homomorphic encryption, implemented as Linux kernel modules, allowed cities to gain insights from aggregate data while protecting individual privacy. The financial industry's adoption of blockchain and distributed ledger technologies continued to accelerate, with central bank digital currencies, CBDCs, becoming commonplace in many countries. These national digital currencies required computing infrastructure that could handle millions of transactions per second while maintaining the security and auditability expected of monetary systems. Linux's performance and security characteristics made it the preferred platform for CBDC infrastructure. Decentralized autonomous organizations, DAOs, evolved from experimental governance mechanisms to legitimate business structures that could manage complex operations without traditional corporate hierarchies. These organizations relied on smart contract platforms and distributed governance systems that required high availability and Byzantine fault tolerance. Linux's clustering and high availability features provided the foundation for DAO infrastructure that could continue operating even when individual nodes failed or were compromised. The concept of computational law emerged as legal systems began incorporating algorithmic decision-making and smart contracts into traditional legal processes. Courts used AI systems to assist with case research and legal analysis, while smart contracts automatically enforced certain types of agreements without human intervention. Linux's auditability and deterministic execution guarantees were essential for these legal applications, where transparency and reproducibility were paramount. Educational systems underwent a fundamental transformation as personalized AI tutors became capable of providing individualized instruction adapted to each student's learning style and pace. These AI education systems required substantial computing resources and sophisticated privacy protections to handle sensitive student data. Linux-based educational platforms provided the security and scalability needed to deploy personalized learning systems at the scale of entire national education systems. The democratization of space access through reusable launch vehicles and space elevators created new opportunities for Linux deployment beyond Earth's atmosphere. Manufacturing facilities in space, mining operations on asteroids, and research stations throughout the solar system all relied on Linux-based computing systems. The ability to customize and optimize these systems for the unique requirements of each mission was essential for the economic viability of space industrialization. Research into faster-than-light communication and exotic physics concepts like wormholes and time manipulation required computing systems that could model phenomena beyond current scientific understanding. While these technologies remained largely theoretical, the simulation and modeling systems used to explore them pushed the boundaries of computational physics and required the most advanced high-performance computing platforms available. Linux's scalability and customizability made it the platform of choice for these cutting-edge research applications. The integration of all these diverse technologies created an increasingly complex and interconnected technological ecosystem. Linux's role as the common foundation beneath this complexity became more important than ever, providing the stability and compatibility needed to integrate systems that spanned multiple domains and technological paradigms. The platform's ability to evolve and adapt while maintaining backward compatibility ensured that investments in Linux-based systems would remain viable even as technology continued to advance at an accelerating pace. As we reach the present day in 2025, Linux stands as perhaps the most successful collaborative project in human history, powering everything from the smartphones in our pockets to the servers that deliver this very text to your screen. The 34-year journey from Linus Torvalds' modest announcement in a university newsgroup to the foundation of the global digital economy represents more than just technological evolution. It embodies the triumph of open collaboration over proprietary control. The current state of Linux development in 2025 reflects both the maturity of the platform and its continued capacity for innovation. The latest Linux kernel releases showcase remarkable advances in security, with Rust integration expanding beyond driver development into critical kernel components, enhanced lockdown modes preventing unauthorized kernel module loading, and memory protection improvements that help eliminate common vulnerabilities like buffer overflows and use-after-free errors. The Linux kernel 6X series, with its performance improvements and enhanced hardware support, demonstrates the platform's evolution to meet the demands of modern computing environments, from data centers to everyday desktop systems. The most recent kernel releases have focused heavily on supporting cutting-edge hardware from AMD, Intel, and NVIDIA, with features like TDX host support for KVM virtual machine isolation and native CPU optimization options that allow users to build kernels specifically tuned for their hardware. The security landscape has become increasingly sophisticated, with Linux facing new challenges that would have been unimaginable during its early years. Advanced persistent threat groups and ransomware operators now specifically target Linux systems, while AI-driven attacks and supply chain compromises represent novel attack vectors that require equally sophisticated defenses. The response from the Linux community has been characteristically thorough and collaborative, with enhanced audit capabilities, improved container security, and hardware-based attestation, providing layers of protection against these evolving threats. The integration of Rust into the Linux kernel represents one of the most significant architectural changes in the platform's history. While C remains the dominant language for kernel development, Rust's memory safety guarantees offer the potential to eliminate entire classes of security vulnerabilities that have plagued systems programming for decades. The gradual rewriting of network drivers and file systems in Rust demonstrates the community's willingness to embrace new technologies when they offer clear benefits, even if the transition requires substantial effort. Recent developments in the Linux ecosystem extend far beyond the kernel itself, with distributions like Linux Mint releasing version 22.1 with improved user experience features, while desktop environments like KDE Plasma continue to evolve with better Wayland support and enhanced file management capabilities. The diversity of the Linux ecosystem remains one of its greatest strengths, allowing different communities to optimize for their specific needs while sharing the benefits of common underlying technologies. The embedded and edge computing markets have become increasingly important for Linux adoption, with the operating system powering everything from Internet of Things devices to autonomous vehicles. The automotive industry's embrace of Linux, through initiatives like Automotive-Grade Linux, demonstrates how the platform has transcended its server and desktop origins to become essential infrastructure for industries where reliability and safety are paramount. Cloud computing continues to be Linux's largest growth market, with the major cloud providers building their entire infrastructures on Linux-based systems. The economics of cloud computing, where providers need to maximize efficiency across millions of virtual machines, make Linux's combination of performance, reliability, and zero licensing costs an obvious choice. The development of cloud-native technologies like Kubernetes and container orchestration platforms has created new opportunities for Linux to enable applications and deployment models that were impossible with traditional operating systems. The artificial intelligence revolution has created unprecedented demand for computational resources, and Linux has emerged as the platform of choice for AI development and deployment. The combination of Linux's scalability, its support for specialized AI hardware, and the availability of open-source machine learning frameworks has made it indispensable for organizations working at the forefront of AI research and applications. The quantum computing field, while still largely experimental, represents another frontier where Linux is establishing an early presence. As quantum computers transition from research tools to practical applications, the need for sophisticated control software that can bridge classical and quantum computing paradigms will only grow. Linux's real-time capabilities and flexible architecture position it well to serve this emerging market. The global nature of Linux development has become even more apparent in recent years, with contributors from every continent working together to advance the platform. The collaborative development model that seemed so radical in 1991 has now become the standard for large-scale software projects, influencing everything from web browsers to programming languages to scientific research tools. The economic impact of Linux is difficult to quantify, but undoubtedly enormous. Conservative estimates suggest that Linux-based infrastructure powers the majority of the world's web servers, cloud platforms, and mobile devices. The cost savings achieved by organizations that have adopted Linux instead of proprietary alternatives likely amount to hundreds of billions of dollars annually, while the innovation enabled by open-source collaboration has created entirely new industries and business models. The educational impact of Linux has been equally profound. Generations of computer science students have learned operating systems concepts by studying and modifying Linux source code. The transparency of open-source development has democratized access to knowledge about how complex software systems are built and maintained, training the engineers who now work throughout the technology industry. Looking toward the future, Linux faces both challenges and opportunities that will test its continued relevance. The increasing importance of security in an interconnected world will require continued vigilance and innovation from the Linux community. The rise of new computing paradigms, from quantum systems to biological computers, will demand new approaches to operating system design that build on Linux's foundational principles while adapting to radically different hardware architectures. The governance and sustainability of open-source projects has become an increasingly important concern as Linux and other open-source technologies become critical infrastructure for the global economy. Ensuring that volunteer contributors and corporate sponsors can continue to work together effectively while maintaining the openness and collaboration that has made Linux successful, will require ongoing attention and evolution of community structures. The story of Linux is ultimately a story about human collaboration and the power of shared knowledge. What began as one student's frustration with existing software has grown into a global community of millions of developers, users, and organizations who have collectively created something far greater than any single company or individual could have achieved alone. The principles that guided Linux's early development remain relevant today: technical excellence over political considerations, openness over secrecy, collaboration over competition, and pragmatism over ideology. These principles have allowed Linux to adapt and thrive through multiple technological revolutions, from the rise of the internet to the emergence of cloud computing to the current AI revolution. As we look to the future, it seems certain that Linux will continue to evolve and adapt to meet new challenges and opportunities. The platform's success has never been guaranteed. It has been earned through the dedicated work of countless individuals who believed that software should be free, that collaboration produces better results than competition, and that transparency leads to more secure and reliable systems. The 34-year journey of Linux from a hobby project to the foundation of the modern digital world demonstrates that revolutionary change can emerge from the most humble beginnings. Linus Torvalds' casual announcement that he was working on a free operating system that won't be big and professional like GNU has proven to be one of the greatest understatements in technological history. Today, as Linux powers the servers that host our social networks, the smartphones that connect us to the world, the cars that transport us, and the satellites that orbit above us, it serves as a testament to the power of human creativity and collaboration. The story of Linux is far from over. It continues to be written every day by developers around the world who carry forward the vision of free, open, and collaborative software development that began in a Helsinki apartment more than 3 decades ago.